Hi everyone. Today we are going to continue our discussion on the graph searches, and we have already seen one graph search algorithm, which is the breadth first search, and we are going to see a new graph search algorithm. But before we go ahead, I'm going to do a slightly longer review for the entire video. This one, if you feel like you still remember everything, and well, feel free to skip this video. Okay, so the first part we talk about the graph presentation. So presentation, we only need to define two set of the objects. One is the edges, and the other one is the vertices, right? And well, depending on how many edges do we have, and we have two different types of the graphs, the dense graph and the sparse graph. So for the dense graph, and the total number of the edges is roughly the number of the vertices squared. So this means if we randomly pick two vertices or two nodes, and it is very likely that there is one edge between them, right? And for the undirected graph, and this means for the edges, and they are the same no matter which way it goes. So the edge from U to V is the same edge from V to U, and then that is a undirected graph. And for the directed graph, and we emphasize on the direction. So we have to say the edge U and V is an edge from the vertex U to the vertex V. Okay, and well, for the for the graph for each of the edge, and we can assign a weight. So a weight can be 0 or 1, saying whether there is an edge between U to V or not. Or we can say, well, the weight from the U to V is a specific value, for example 10. In this case, 10 will be the weight of the edge. So the next thing, well, how do we represent a graph using a data structure? So the easiest thing is we create a n by n matrix, and n will be the total number of the vertices. So if we have the vertex 1, vertex 2, and all the way to vertex n, and then to represent the possible edges, and then we have to create an n by n matrix. Okay, and in this n by n matrix, and aij is 1 if there is indeed an edge from I to j, and otherwise there will be a 0. The problem with the adjacency matrix is, well, if we have to store the graph with n nodes, and then we have to create a n by n memory space. So it works well with a small graph, but if you have thousands or millions of the vertices, and then it will take too much of the memory space. Oops. And then, well, the next thing is, well, if we want to do the graph searching. So for the graph searching, actually we want to achieve two different goals at the same time. And the goal one is we want to explore every vertices, and then and every edge. So this is the first goal. And the second goal is, well, we also want to create a tree structure. So we want to keep definitely all the nodes, but we don't want to keep all the edges. We want to pick part of the edges, and then we want to create a tree structure. And if it doesn't work because several parts of the tree or several parts of the graph, they're not connected, and then it's not doable with just one tree, and in this case we have to create a forest. Okay, and this is the breadth first search we have talked last time, and the strategy is we want to visit one vertex at a time, and then we want to explore the boundary of our search across the breadth of the frontier. Okay, and also we on the fly we want to build a tree structure, and we want to make use of the different colors. So at the very beginning we color all the vertices to be white. So a white node means, well, it has not been discovered. And then if we have discovered a node, and then that node hasn't been fully explored yet, and then it is a gray vertices. and then eventually, if we have finished explore the current node and then all the direct vertices connected, and then we will color the node to be black. Okay, and then if we want to search, do a breeze search, breeze first search for this one, and then we specify we want to start the search as a S. So to set this up, and at the very beginning, we color all the nodes to be white. And after that, well, we send the root, which is S, to the queue. And remember, when we are doing the breeze first search, we are making use of a queue data structure. So a queue is the data structure allows us to do the first in, first out, right? So, and then we are going to iteratively pop one from the queue, and then we explore all the adjacent white nodes. Okay, so if we want to pop this, pop the S up, and then we explore all the adjacent white nodes, and then we have the R and W. So we have the W and R put into the queue, and then we highlight those two edges with red, saying those two edges will be used in the tree structure. And after that, S will be changed to black because now we have finished visiting S, and then we have also finished exploring all the adjacent white nodes, right? So the next one, we want to pop up another one from the head of the queue, which is W. So we pop up W, and then for the two adjacent white nodes, which are T and X, we add them to the queue. And then after that, we have explored all the adjacent white nodes of W, and then we say, okay, W can be black now. And the next node, which is the front of the queue, will be R. So we pop R out, and then we add V to the queue because V is the next node adjacent to R, and that is also in white color. So we pop R out, and then we put the V here, and then we highlight this edge with red color, saying this edge will be taken into the tree structure we generate. And after that, T will be the next. So T is connect to U, and the U is already is a white node. So we want to pop up T, and then put the U in the queue, and then T is black. So in this case, when we are exploring the adjacent nodes of T, and you see there is U, and then we have already added the U to the queue. And however, W is also an adjacent node to T. But since W is in black color, this means W has already been explored, and we have already finished exploring W. So we don't want to put W into the queue again here. And the similar thing for X. So for the X, it is gray, right? It is gray means we have already discovered the gray node X. However, we haven't finished visiting that yet. And in this case, we see X is an adjacent node to T, but the color is gray. So this means this X, we don't have to add that to the queue again because that X is already in the queue. So when we are doing the exploration, we only want to visit white nodes and then add the white nodes to the queue. And after that, the next thing we are going to visit will be X. So for the X, the only adjacent Y node we haven't discovered yet is the Y. So we put Y to the queue, and then X is popped out and colored into black. And eventually, we visit V, and then there's nothing new we can add. We visit U, there's nothing new, and we visit Y, there's nothing new. So eventually the queue is empty, and then we have colored all the nodes into black color, right? Okay, and for the breeze first search, instead of it help us to visit all the edges and all the nodes, and then it also generates a tree structure for us. But in addition, breeze first search will calculate the shortest path distance from any node to the source node, and for the source node, and that is just the tree root, right? So for any node, and for example like this Y, so it's there is a 3 here. And this means from y, if we want to go back to the root, so we will have to follow the red passes. So y to x, one hop, x to w, another hop, and then w to s, another hop. So there are a total of 3 hops that we can go from the y to the s, and that is the shortest path guaranteed. Okay, and when we are doing the breadth first search, and the time complexity will be the O of the V plus E, and then V is how many vertices we have, and E is how many edges we have. Okay, so that is a short review for what we have learned so far, and then the next video we are going to move on to the depth first search. Okay.